right. Can everyone hear me? Looks like we got a couple people still trickling in. Uh, Welcome back to United Astronomy Clubs of New Jersey. For once again, it's a lovely hot day outside, slightly hazy. We're just getting a couple people settled here. I see people coming down from from our observatories and hanging out on the rock. So while I'm waiting for a couple people to file in, I want to welcome you all. You can check, we are live streaming this to our YouTube, and if you happen to miss it or come in the middle, you can always check us out, replay the broadcast through our YouTube. We do keep those there. In addition, you can check us out on our website, uacnj.org. You can get information on all of our member clubs, what programs are coming up next, as well as what any special events we may do. We are a nonprofit organization. Everyone you see here helping is here on their own time, and every improvement you've seen made through the stream or to our grounds has been made possible from donations from people like you guys here on site or watching. You can donate through our website. We also have the Patreon. In addition, we have a couple social media. We got our Facebook, Instagram, Twitter. We got a Discord server. And all of that you can check out, view through our website as well. So, a couple things for the people here. If you do need to use the bathroom, we got the porta potty to my right, your left. It has the red light on it so that it's not completely dark when it gets dark. We do have the gift shop available. I'll be running that after stream. It also has a small museum area where you can check out where we have meteorites and whatnot. So tonight's presentation is about the James Webb Telescope, the past, the present, and the future. So we got Michael Dean Lewis here, who is an active NASA Solar System ambassador. He regularly participates in teleconferences. Gotta get my from being wrapped around my eye tooth so I can see where I'm talking. He's presented those teleconferences presented by NASA scientists and loves to present programs to a very public audience. He lives in Hillsborough, New Jersey, and is a return guest speaker here at United Astronomy Clubs of New Jersey. And with that, we are going to get started into our presentation, and here is Michael.
I have the opportunity to see pictures and photos of the James Webb Telescope, and behind the scenes that you will not be able to see online. I don't know why, but there is an active website though on the NASA website for the JWST. We call it the JWST, the James Webb Space Telescope. It's a lot less to say the acronym than it is to say the whole thing over and over again. But if you've been following the news, the telescope has been front page news for the past 5.5 months since it was launched on December 25th. When I was in Florida at that time when it was launched, that was pretty cool. And it got successfully into not orbit, but into its trajectory, so that it entered into a mobile, stationary, quasi-stable position called the Lagrangian point. We'll talk about that in a moment. The past of the telescope was conceived after Hubble was launched, but it was built and designated to be it is the replacement for the Hubble Space Telescope. We remember very well what happened in the 80s when in 1986, the Hubble was supposed to go up, and then we had the terrible tragedy of the disaster with Challenger. I was at Rutgers at the time, graduate school, in a mathematical physics class, when I got the news that I had heard that Hubble, that not the Challenger had blown up, because I'd heard in the morning when they gave a report that Challenger wasn't to launch that morning; it was too cold. And of course, we found out later from Richard Feynman and the committee about the O-ring, and in fact, it was too cold, and the O-ring had shrunk. But regardless, the Hubble spacecraft finally made it up 6 years later, and has been in operation since. Now that's the past. But in order to replace it, those began to looking at where were the weaknesses of what the Hubble had, and so James Webb at the time, he was alive. He is this well-known person within the NASA community. He was the second administrator of NASA, and he oversaw many missions of unmanned and manned from the beginning of the space program. And so this telescope has got a lot of like prestige on it, because this Webb was such a powerful person. Now there's another guy who's going to also get honored in the years ahead. His name's Ed Stone, who I've known for a while. I've been with the NASA Solar System program since 1996. So this is actually my 26th. And if you go on the website, you'll see that there's over 1,000 ambassadors now around the world. And when I first began, there were 13 of us. 13. We used to present to, like we do now, to astronomy clubs and space museums and museums in general, and to high schools, middle schools, and elementary schools. I do that in my part-time. It's a lot of fun because I get to see the stuff that most people don't know about at first, and then you get a blurb on the paper or on the internet now. And it was Webb who insisted that space science continue and be a strong part of unmanned missions, and so we honored him for that. Okay, so I want to get through some slides pretty quickly. Here is a picture of an artist's rendition of the Hubble spacecraft, and you can see here it's got some sort of hexagonal dimensional gold thing with a tripod that we use on our telescopes on Earth sticking out from that, and then behind it in the blue there's something there that's hanging down. Okay, so that's a graphic demonstration of this. This from 2014, this slide, believe it or not. And then here you have the Hubble Space Telescope, which is in near Earth orbit. Right. And I like to do the thing about how far is Hubble from us on the Earth when it's near Earth. How many miles away is it? And that's one of the questions that I like to ask. Does anybody know about how far away the Hubble is as it goes around the Earth? Yeah, go ahead. How many? A what away? A week away. Oh yeah, in space. Right, a week in space. Well, let's say if you were driving a car, and you were driving to Cape May. You know where Cape May, New Jersey is. I hope everybody knows where that is. From here, you would reach the Hubble spacecraft. That's how close it is. Yeah, it goes around the Earth many times in a day, on the order of 18 times a day. Yeah, traveling at about 18,000 miles an hour. So you can just do the math and figure out about how many times it goes around. But it's a testimony to the technology that we've been able to keep Hubble up for, this is now what, its 30th year. And many questions that had been asked as we look around and we see the telescopes that we have at Jenny Jump, right? And you look at the picture here of Hubble, I don't know if you can see it that clearly in the background. It looks like a huge, just an elongated telescope sent up to Earth. We'll look at the comparisons of it soon. But the amount of scientific knowledge that the Hubble has given us is quite extensive, and it's driven the need to learn more and more. All right, so from the Hubble, we've been able to learn of the deep space field, where if we look in the night sky from Earth and we see a blank place in the sky where it looks like there's nothing there, that is not true. What Hubble saw here in the deep space field is what has caused us to change our viewpoint about our universe where we live, where we're moving through. And I'm not going to get into the complexity of how the Earth is going around the sun, and the sun is moving through the Milky Way galaxy, taking about 225 million years to go around, and how the Milky Way galaxy is moving in a local group. There's a lot of space science out there, and we're wondering, how can we travel further? And how can we learn more about outer space? The Space Telescope, the Webb Space Telescope, will lead us even further than Hubble. And as you can see here, that looks like a pretty cool picture. And instead of seeing nothing out there, we're seeing thousands, literally thousands of galaxies, where there are billions of stars in each one of those little bright dots. Okay, so what we do when we look at a space photo like that, we look at what's called the redshift. And we're going to talk about redshift in a little bit. Now, redshift is something that corresponds to an object on Earth. There's something called the Doppler shift, where if you have a redshift, it's as if you're hearing the object making a sound traveling further away, and we notice that the tone, the pitch of the frequency of the sound decreases. And if the pitch of the sound comes towards us, we call that a blue shift, or an increase in the pitch. And we notice that this is with the stars. The stars traveling away or towards us. Of course, the discovery that the universe was expanding was one of those things that made by Saul Perlmutter. He came out of the blue. He was not even a space scientist, but he was able to use telescopic, on Earth-based telescopes, information that was being fed through computer of these supernova, and we found that for some reason, we don't know why, Ed Witten, who I've had the pleasure of being with from Princeton, and is also this real well-known astrophysicist, we don't know why the universe is expanding, but we know that it is, and all measurements point to something that's like a vacuum that's pulling the stars out further. Well, Webb is poised to take a look at that, besides some other things. Anyway, just some information here about the redshift. If you have a number 3, that would give us information about the age of the universe. If you have a redshift of 10, that would correspond that the universe is traveling even slower. As MYR is millions of years, and GYR is gigayears. Okay, so we do care about the redshift. I just want to get into that a little bit. That the Webb telescope will be even better in showing how much of a change that the universe is dimming as these stars travel away. The telescope will be looking at the stars. Okay, so here's a nice picture here of Hubble, and Hubble is on the left, and you have the Webb telescope on the right. And you can see that the Webb is larger. It's bigger, and there's some other information that's provided given here about the diameter of the telescope for Hubble is about 2.4 meters, and the width of that gold shield that you see there, it looks like that is the mirrors on the Webb, is 6.5 meters. 6.5 meters, that's about 20 feet. You can see here that the mass of Hubble was over 12,000 kilograms, but the mass for the Webb telescope is 6,200 kilograms. And you can see here the wavelength range where Hubble had a 115 nanometer to 2.5 micrometer. Now you might not get that. I'll explain a little more. But the wavelength range for the Webb telescope is much smaller. It extends from 0.6 to 28.5 micrometers. All right, so this is looking at infrared. Infrared is where we're trying to find out what's happening with heat signatures. The operating temperature of Hubble is 20 degrees C, but while we can really cool down the James Webb telescope. Okay, and so here you have the orbit of the Hubble. This is really what's amazing, is that it's in near-Earth orbit. It's 550 kilometers, like I said, it's about 300 miles away, while the orbit of the L2 is 1.5 million kilometers away. We'll get into the Lagrangian points in a moment. But this is not the first time that we've gone to the Lagrangian points, right? But it is one of those things that it has. It's really an amazing thing that we can do that. All right, so let's take a look at some more stuff here with the telescopes. Okay, so here is the telescope as it's being oriented, and you can see here the different. It has an optical telescope, primary, secondary mirror. It's got a back plate. It's got the sun shield. Has an integrated science instrument model. It's got all these modules, and when you see this, this presentation, and you see the video that you're now looking at, the telescope when it first went out was compressed. It was like a box, and during the months up until March, it had to be unfolded, and each mirror had to be tested and aligned, which is it's amazing. It's 24/7. My niece is working at Jet Propulsion Laboratory. She graduated from Stanford 2 years ago with her PhD in astrobiology. So she got hired by JPL. These operations, when they're doing them, they're 24/7, 365. Right now, there's a crew of like 20 or so personnel who are manning the monitors, and they'll be shift work. They go on like for 8-9 hours, and then they're off, come back the next day, around the clock. And it is like working a manufacturing plant, if you know what I'm talking about there, some of your elders, where they're constantly monitoring what's going on in outer space, right? And so I'm not going to talk about the Deep Space Network or how we communicate with it too much. I mean, Deep Space Network is one of those amazing facilities where we have these radar dishes, and they're solely dedicated to obtaining the data from the James Webb Telescope and other missions that we have, like a Mars. We have the Perseverance. The complexity, the detail that we get. I don't know if everybody appreciates or realizes how far we've technologically advanced ourselves in the past few years, just as we've seen the computers and they're being more and more adept at doing calculations and figuring out what's going on whenever we ask them to do things. It's the same thing with unmanned spacecraft. We can put that hardware, those computer systems, immediately, that day. Oh, we got a new we got a new DOS system. We've got a new computer. We got a new IC, integrated chip. We have a dedicated circuit analysis now that we can, and we don't have to wait. With manned spacecraft, we can't do that, right? So this is one of the things that we get. So with this telescope, we get this loop video that's showing the different things that the Webb has. Okay, so one of the things that it has, it required the technology because we knew we were advancing that way. And you can see here the different systems that are involved: micro shutters, the cryocooler, the backplane, the sun shield coating, cryogenics ASICs. That's the integrated circuit. That's a autonomous circuit that it's specific to every part of the panoply of instruments that are there. And we'll talk more about what these slides, what these different parts are as we go on. And we'll just take a look at what the hardware really looks like. Okay, so this is a Jet Propulsion Lab, and these are clean rooms. Jet Propulsion Lab, Caltech, that is where the clean room began. I don't know if any of you know the history of the clean room. It was begun as a sidelight from a guy named Claire Pattison, who wanted to find out the age of the Earth. At Jet Propulsion Lab, he was the first one that came up with a clean room. Now clean rooms are widely used in so many industries, but he had to get the lead out of the air. I don't know, the older ones who were my age, born in the 60s, 50s, and earlier, even the 70s, had to deal with gasoline that was had added to it a thing called tetraethyl lead. And when Patterson was doing his research, he couldn't get the lead out of the samples. It drove him literally years into finding out why. And of course, when he was at the University of Chicago, they moved to California, he was able to begin this thing called the clean room, which you see here, where the air is constantly being filtered, where you can't even get a hair in there. Bacteria, forget about it. The clean room is one of those places where they go in there, and these instruments are beyond what normally we would ever think of, of what you think is cleaning your room, right? So don't get too upset, kids, when your parents tell you that your room needs to be clean. Just say, I'm not going to make this a clean room. That's beyond me. You can help, though. Okay, something like that. But anyway, so this is where they assemble the equipment, okay? Of course, but before that, right, the design has to be done. And that's another part of our development, right? The way that we design everything now is done computer-wise. Here I am presenting on a PowerPoint. I don't have my slides that I used to give, and we go around. We have the carousel. You get the pictures, right? So the past and the present. So here we are in the present, and you can see how they're working together. You have these huge rooms where it's so clean, and they're assembling the mirrors. The teamwork involved, amazing. We'll get into that in just a little bit. But the mirror technology, we learned quite a lot from the mistake of Hubble, right? And each of these mirrors that you'll see here, the many mirrors that are there, they're each coated in a very thin layer, about 1,000 atoms thick. That's around 100 nanometers of gold. And why is that used? Because it is the best reflector of infrared radiation. And this is all done in vacuum. And it's done on amorphous glass. And it's done at a very cold temperature. Very precisely done. They used approximately 270 kilograms of the glass. And of course, the thin layer though it's very thin. It doesn't amount to much mass at all. A few kilograms of gold. Okay, so here is the main frame, like a car body, without the panels on the outside. This is a good picture of the space telescope structure, where the mirrors and the instruments have to be attached. All right, so you can see it looks sort of like a ladder on one side, and then you've got these interconnecting bits like a Lego set, right? And you got the all of these designs are made in relation to the instruments that are going to be attached, and then they have to be attached so that the system will hold together for years, not just for a few months. All right, and so the same technology has been applied to the Mars orbiters. To, for instance, we still have a Mars orbiter from 2001 that's going around the Odyssey orbiter, right? That's 21 years now. Um, and we have of course, the unmanned robots that are on there, and we even have a drone on Mars, Perseverance, and that Ingenuity drone, still functioning when it wasn't supposed to be functioning. Right, and it's been over a year on the surface of Mars because we prepare ahead of time. Now, when I first joined the NASA program, that in 1996, we had suffered two significant failures, and I talk about them in every presentation when we're looking at outer space, because we had this thing called the Mars Climate Orbiter and the Mars Polar Lander, and they were going to that time the internet crunch was happening. That is that the bubble, the internet bubble was popping, and there wasn't the funding, and because of those two failures, there was a lot of talk about that we were going to do away with all these programs that had been planned. So the group at JPL and the headquarters, they came together, all the labs did really, and they made a significant attitude adjustment. And so since then, we haven't had one failure. Okay, in all these missions, we're talking about dozens in outer space. So it's one thing. The United States, we've done great upon. But anyway, here's a comparison of Hubble, 2.4 meters, like I said earlier, to the 6.5 meter. Um, okay, so the big difference with Hubble and the Webb, I would say the largest difference is where they're located. The Hubble is near Earth orbit. Like I said, you could drive there in a few hours if you were driving into outer space, but not the Webb. The Webb is located almost 1 million miles away, and because of that, it is in a place where it needs to be continually protected from the sun and the solar radiation. It never gets too hot, but again, it can get very, very cold. So it must be protected out there, and it has to be self-sustaining. We go up and service the Hubble Space Telescope. We don't do that with the Webb telescope, at least not yet. I'm kind of excited that that might happen in the future, that we may be sending astronauts out to where the Webb is, within that Lagrangian point. But that's yet to be seen. Okay, so here we have the spacecraft coming together, and you can see how now you don't really see the frame, the basic frame, as well. All right, and of course, now we're going to show the team and how large it actually is. All right, so if you do go on the website and you go check out the people who are involved, you can see how large the Webb telescope is to the group that are there. You'll be amazed if you go to the site where how was the telescope assembled? You know, how did that happen? And you'll see that they transported this thing back and forth to many places in the United States. Many places. Here on the map, you'll see there's in New Jersey. We had the Webb was in Moorestown. You know where Moorestown is, I hope. Just outside of Philly, right? About maybe 20 miles out of Philly. The Webb was there. Yeah, and they did at Lockheed. They did some work there on it, and then it got sent out from there to another place. So this teamwork, just an amazing amount of people just corroborating and getting it done, making sure it gets done. And so finally, the initial launch was to be in March of 21. Of course, we know because of the COVID and the need to hunker down, there was a slowdown, and it wasn't until December 25 of last year that 9 months later, fortunate anyway, that the spacecraft was launched. It was not launched from the United States. It was launched from South America, French Guiana, and it was a great launch. Right, it got out, and now let's take a look at where it is. This is a picture looking down on our solar system, and you can see the Earth, you can see the moon, you can see the sun. Sun's in the middle, and you can see those white dots that are around. Those are called Lagrangian points, and a Lagrangian point is where the objects, the space objects like the moon, the Earth, the sun, pull on equally with their gravity an object, and that object, wherever at the Lagrangian point, is able to stay there in orbit around the sun as it were a planet or a satellite of the sun. And we're at L2. Now, you might want to know why do we pick L2? There's five of them. Let's look at L5, right? L5, there's no one around. There's nothing around. L5 is out there beyond the sun, on the other side, what we call a conjunction, right? Opposite. And why don't we put it there? But think about the sun, right? The sun is continually spewing out its solar wind, so that's a dangerous place, and also it's not that stable. The Lagrangian points are sort of stable. The 1 and the 2, they're what we call they're semi-stable, but the object will stay there if you keep it in motion, and we'll find that the Webb telescope is moving. It's moving in a little orbit perpendicular to the orbit around the sun to stay in the Lagrangian, but it doesn't require any energy. It just keeps looping. That's in the L2. Now the L2, why would we pick L2? Well, the L2 is behind the Earth, right? And so we do get blockage from the Earth on the solar wind, say, solar rays. If we put it in L1, it wouldn't have any. The Earth would not be able to block that wind as well. And the most stable points are the L3 and the L4, the Lagrangian points, where that's where we might put something for going very fast with laser propulsion. I don't know if you've been following all that. How can we quickly move a spacecraft in outer space? That's by using like solar rays, where power up, we got laser, beam the laser at a spacecraft and let that spacecraft keep accelerating. Anyway, that's another story. We could do that now, by the way. But all right, so L4 and L5, and you can see here that that's 1.5 kilometers away, L2, which is about 1,000,000 miles. All right, so here's a just video. You can see that the object, the telescope, will just keep orbiting as the Earth orbits. The same period, we say, the same time period. We just say period. Yeah, and comes in and out a little bit, and that Lagrangian point. Okay. So here again, showing that with the Earth between and the Sun to the spacecraft, you get a little more protection from the solar wind. Okay, as the moon goes around. Okay, so here's some pictures of the gold reflectivity, the importance of the light bouncing off these mirrors, and it bounces off 5 mirrors before entering any of the instruments on the JWST. All right, so that's another thing that you might not get that unless you hear from somebody like me, right? But each of the 4 main scientific instruments, you have to have the 5 mirrors working together, and we have aluminum as well. Let's see, but no, it's the gold that it helps. Okay, so this is looking forward. This one, the Space Telescope Institute, back in September of 2014, we were looking at the science here. And here's a picture from that where the concept was that we would have the largest cryogenic telescope ever constructed, and it would be 100 times more sensitive than the Hubble, and it would have 10 times the image sharpness of Hubble. And as you saw, it does go out to about 27 microns. And here's a comparison HST. That's on the bottom. You get the light gathering power between 0.1 and 1, and the JWST is from 1 to about 10 microns. So there you go. That's just to show how much technology has advanced in that time. Okay, so here's what happens when you cool down the mirror. All right, so on the one on the left, that would be ambient temperature, meaning the surrounding temperature. Normal, that's how many flaws you would see in the mirror. When you cool it down, you see how smooth that hexagonal is, meaning that the reflections are almost perfect, right? And there are ways that we fine structure the mirror. We have the primary, the secondary, the tertiary, and the fine steering mirror. And then that, if you've been following the news, the mirror has just been completely aligned, right? So this is present. This is the present. So we talked about the past and the present, building it up, and now we're getting to the point where, and I hope that I'm invited back in August if there's an opening where I can show lots of pictures. I'll be like one of the first that ever gets to see them. That's one of the things, I got picked for this thing back in '96, and I've continued with it ever since, because one of the things that drives me is that I get the stuff, first, right? I'm the one of those. I get the. I may not be part of it. I'm like the salesman who gets the new Corvette coming into the showroom, but I get to drive it. I get to handle it. I know what's happening with it, and that's what it's like when I get these slides, and I get to share them with you. Anyway, there's the mirror. And then again, here's the rendition of what it looks like. We'll move on. Here are the different mirrors, and you can count them out, how many there are. But they're numbered and labeled. They're alphanumeric. You got an A1, A2, A3, A4, A5. You have a B1, B2, B3, B4, B5, and a B6, and a B7, and a B8, right? And then you have the C. C1, C2, around to the C6. So you can count up those, and you can see how many there are, right? There's like 5, right? 9, right? 10, 14, right? There's 18? Yeah, 18. So there they are, and they're all working on the infrared, right? Infrared, essentially the heat wave. It's the heat wave. And if you look here on this picture, the infrared is the red part. uh, right here. I'll just put the cursor on there, and you can see that's infrared. And we're feeling infrared tonight. Yay! First time we've had hot temperatures all year. Yeah, and we got clear skies. So after the presentation, we can go and look. And I don't mean to say anything. I don't know if it's coincidence or whatever, but it seems like if you have been to my presentations before here, it's always been a clear night. I'm not kidding. I don't know. I've been here like what, 5, 6 times, I don't know, and it's always been clear. So keep inviting me. It'll be clear. No, no, next time it'll rain, but no. Let's hope it'll continue. So anyway, so we're interested in infrared. You might want to know, why is infrared so much more important than optical? Well, it's because you look at this picture here of this gentleman, and he's looking at a piece of plastic here in front of him. Infrared can see through where visible light can't. And you can see here he's got this black bag there, and he's got his arm in there. You don't know that, but I'm telling you that he's got his arm in there. That's with visible light. And now we'll take a look at infrared, and you can see. You see? You can see right through him. Now, this is one of the things with the mathematics. You can take an infrared and change it into an optical. And we'll do that, invisible. Say, yeah, just like you saw the visible, right? You saw the visible. Well, now we see the infrared. Well, we can convert that, right, back to visible. We can't do it the other way around, though. Can't do it the other way around. And so we can see through the galaxy. We can see through other galaxies. We can through these clouds. We can see through the clouds. We have these star systems where they've had their supernovas, and we can, like the Rosetta, and we can look up there where the pillar is, the Eagle Nebula, for instance, and now we'll be able to look into it with this redshift and blueshift, and we can actually now we'll be able to define even further what's going on with these stars within these clouds, whether they're moving towards us or away from us, and how fast are they moving, etc., where we couldn't even see them before. And of course, then this leads us to the age and how we can maybe see the first galaxies forming, because we have to see through all that. It's like a curtain, and we can now, with these long exposure times, look right through the curtain, back into time, back to where there was this singularity we call the Big Bang, and maybe we'll find out more about that singularity. We've heard talks about multiverses, and that when we get into the quantum level, that means the real small level. For those where everything is stepwise, that there's questions about why we can't determine at that level what's going on. There's that uncertainty. Okay, so here are the 4 big science instruments. We get all this because I know we're running short on time. Here are the MIRI, the NIRIS, the FGS, the NIRCam, and the NIRS. We'll talk about those. All right, and they need to have a guidance sensor, a specialized camera that is looking around at the stars to make sure that the spacecraft is staying in the Lagrangian. Like I said, it's sort of unstable at that position, so it has to be modified. All right, so there's 2 parts here. There's the short wavelength and the long wavelength channels, right? And so we look at the long wavelengths. Those will allow us to see even further into the dust, and then they have the shorter wavelengths. Okay, excuse me. All right. So here is the optical layout of the way that the spacecraft operates, and it channels the light beams into the different instruments, and it splits them. So it takes that one beam from those 5 mirrors and is able to process it. And all of this, of course, is in contact with the Earth. There is a slight time delay but it's not that long between the telescope and ground. And so here's some more of the optics of how the instruments were tested and retested, how they were enclosed, how the filters were put in front. And near means near infrared camera. Filter wheels slots up to 12 filters, so we can look at different ranges of the infrared. And here they are assembled. So Module A and Module B, they're mirror images of each other, believe it or not. If you look at it carefully, they look almost the same, but they're enantiomers. One's right-handed, one's left-handed. All right, so here you have, this is a little technical here, where the near-infrared camera, it talks about the two channels in each of those, the left one and the right one, where one channel is short wavelength, the other channel is long wavelength. You get the filters that gets to even spread out the frequencies even more, and then you have the gaps between them, the between the A and B, the distance between the different parts. Okay, so there. And this one again is just shows the wavelength. All right, comparing the Spitzer Space Telescope with the Hubble Space Telescope. Spitzer was another telescope that we had put up earlier, but it was also very helpful. It was in a different infrared range, but you could see here that the near cam on the JWST broader, and this is the comparison of with that wavelength. So when we say NJY, that's short for nanojansky, and a Jansky is the amount of brightness. So for the Spitzer Space Telescope above, you can see those lines going across. It had to have between 10 to 1,000 nanojanskys of brightness to be seen. But with the JWST, you can see there that it almost goes to 0 of brightness if it's extended at that wavelength of 1.4 microns, right? And then you can see that across the band, the sensitivity is almost an order of magnitude better for the Webb telescope than it is for the Hubble Space Telescope. That's the one in green. So when they do these long observations, they'll have them last a day, half a day. The NIRCam will be about 10 times more sensitive, like I said, than the Hubble. All right, so a nanojansky, just to give you an idea, it's like a candle at the distance of Jupiter, right? So if you're at 1, this is the amazing thing, right? 1 nanojansky. If you had a candle burning out by Jupiter, that's a candle. That's just a candle, like one of the homes, right? That's the nanojansky. You can see here that the Webb telescope is very, very sensitive to light, to brightness. Okay, so here's a comparison, what we expect we'll be seeing with the simulated. If you look carefully here, you just see how on the right, there's a cloud, right? And from further away, they look almost the same. But as you look at the bottom one with the JWST, you can actually see the stars, individual dots. Okay, we're getting there. Also, what else will be happening? Here are the 4 main goals. End of the dark ages, when we first see the light. I've talked about that with the end of the Big Bang. And then we have the assembly of the galaxies. We should be able to see that. Also, we're going to witness the birth of stars and protoplanetary systems and planetary systems and the origins of life, which we hope that we'll be able to get something there. Also, with the galaxies, here you can see the picture above here in the blue and the green. That was done by the Big Bang. That was the cosmic background radiation study, and that was done from Princeton. And you can see here the disparities of the blue and the green and the yellow, the different colors. And if you look carefully, you'll even see a little red. And that shows the birth of that was just further confirmation of the Big Bang. That did not lead, though, surprisingly, to showing that the universe was expanding. That was not shown in that picture. That picture just shows that there was this disparity in the temperatures, and the only explanation that could cause that was a singularity that occurred at the beginning. All right. And so we have these gravities causing the densest filaments at points to collapse. We're going to learn more about how the stars are forming. And here's a nice picture. We're going to hopefully get to find out where are the first galaxies. And that's where that redshift comes into play. Those will have a big redshift. They should be billions of years away now. And then looking at how the objects ionize. Now we know that when the universe first formed, that there was this plasma that occurred, but how charged was it? Was it? It's a window there. There's a window. There's a curtain over that, where we eventually in time we know that the protons and the neutrons and the electrons, they formed, and then we began to have hydrogen, which is the most common element in the universe occurring. But when did that occur, and how did that occur? Let's see if the models that we predicted are true, and the Webb will prove that. And I kind of would like to compare this to when we started with the New Horizons. Those of you who are familiar with the Pluto mission. Back in the day, right? Pluto, what was Pluto? It wasn't even a planet, right? I mean, it was a planet. Of course, that all ended in 2006 with Mike Brown and the rest of the astronauts. They said it's not big enough. Right? Still, some of us are calling for it to come back. It's just historical. But the point being that we had no idea what it was like, and now we know that there's a heart on Pluto. And there's all these different features on the planet, and it's internally warm inside, and the orbits of these satellites that go around, Hydra and them. And I know I've presented here a couple times on New Horizons, and then going out to the Kuiper Belt, right? These are fantastic discoveries that we've done, and now we're going to learn about the universe more, and how these nebula and clouds, what's going on inside them, right? This is what Webb will show us. The first light, the assemblies of the galaxies. It's going to be really cool when you can one of our telescopes here out into Orion and see the belt of Orion and see the Eagle Nebula there. That's the picture that you see here with those stars, but we don't see really within, not too much. Now we'll be able to see the interstellar clouds, how they collapse to form stars. We'll be able to witness that stuff, how the gaseous disks form around stars, how do planets condense out of them. Why? Because we haven't been able to see through the clouds. We didn't have something that was able to. Close, but not close enough. Now we'll be able to. And objects like this that we see here with the Eagle Nebula, as seen in the infrared, will be even further defined. We'll look at planetary systems and how are these habitable zones established, right? We had the Kepler spacecraft up. I remember when the first planet was discovered, extrasolar planet. People used to laugh at me or laugh at people that said, oh, there's no such thing as extrasolar. Forget about that. And then the first one was found. It was like, wow, we're right. It was there, and it's going to continue. We've now found thousands of extrasolar planets, and there's about 70 of them that we know that are what we call the Goldilocks zone, where the planet could sustain similar atmosphere because of the distance from the sun and the orbit, the length of the orbit around the sun, the period. And that is what this the web will give us. It will give us this information. I'm not being excited, as I present this habitable zones and all that. All these 18 mirrors, right? They're slightly misaligned, but now they're aligned. Let's talk about the present. And we just saw a little bit about the future. And now that all these sensors have been there, they're going to start presenting us more and more with the information, these photos that we'll be getting. All right, now maybe some of you have questions. Here are some online resources if you want to come up, take a picture of that later, and I'm done. I'll give you that, where you can look at some other off-sites where there's a lot of information. Here's another one about where there is tech applications and all of these, the four instruments here. And then a little bit more about who's behind the web. We're getting short on time. But you may be asking me a question about, you recently seen the black hole pictures of the galaxy, the Milky Way galaxy, that came about. It was presented, I think, like 2 weeks ago, where we could actually see that there was a black hole there, and you could see the horizontal line of the hole, and they had the three blobs that were going around the black hole. Well, the Webb will be able to show us into the center of the Milky Way better than any other telescope so far, but it won't be able to define the black hole. That's just, we don't, that's almost impossible anyway, because it's 60,000 light years away. If you didn't know, we're about 60,000 light years away from the center of the Milky Way. But we will be able to see the stars that are orbiting the black hole. See, that's what's really going to be cool. And you can read about that, and there's videos of it on YouTube, where the Dr. Becky, she's pretty cool. She's an Irish lass who was working at the University of Oxford. She really likes to present stuff on astrophysics and astronomy. So I recommend that you do that. Okay, so that's about it for today. Are there any questions from the audience?
Right. Before we get into our question and answer session, I want to thank you, Michael, for coming to speak with us again. And I wanted to thank you guys and our online audience for also joining us. I noticed a couple of you did file in during our presentation, so just to go over a couple safety notes. If you need to the restroom, it is to my right, your left, with the red light on it. We do have a little gift shop area with a little bit of a museum attached in the door to my left, your right. Each of those sheds that you saw when you came in does house a telescope. It looks like we have a number of them out tonight. I do ask that if you are not feeling well, you do be mindful of how you are interacting with the telescope. If you're not feeling well, possibly don't touch them. That being said, I do think there's also a couple scopes out on the lawn. I do know at least one of them is not one of UACNJ's telescopes, so I ask that you ask permission before trying to view through those telescopes. If you see anyone with a name tag and they're running a telescope, please do go up to them, ask questions, and they'll be able to tell you what they might have their telescope pointed at. Right, with that, when you do go to leave, please use your headlights, because we don't like getting run over. Been there, done that, wasn't fun, would not suggest. That being said, if you do have a flashlight or whatnot for walking, please keep your light pointed towards the ground, because even though headlights are very useful for not running people over, we don't need the extraneous other lights possibly blinding people. Right. So with that, we're going to get into our question answer session. I ask that for the people here, if you have a question, raise your hand and kind of wave it around, because it is dark and I have trouble seeing, which is why I have the glasses. But to get things going, I I have one question from our online audience, and then I'll get one from you guys. So the first question is, how did you get involved in being a NASA space ambassador?
Oh, that's a good question. Well, it happened. I was teaching a physics class in 1995, and at that time there was a spacecraft called Galileo that had been arriving. It had been en route for about 3.5 years. We have to get used to these distances and the time travel it takes. And the Galileo had a probe that was launched from it, and at the time it was the fastest moving object being attracted to the gravity of Jupiter over 1,000 miles per hour into the atmosphere. Well, I was interested in that. This was the beginning of the internet at the time, 95, right? And there was a fellow named Ron Bell. He presented some images of Jupiter, and I sent him an email. I said, Ron, your images aren't exactly correct. They're not showing the perspective. And he wrote me back, and he explained to me that he wanted to show this way. And after that, we continued, and it led to conversations with other people with NASA. And they said, well, would you want to present? And at that time, I was then called an ambassador from Jupiter. Yeah, so I was from Jupiter. They changed it then to Solar System Ambassador. They realized that it could be expanded. That's how I began, and it
Uh,
continues to the day.
all right. Was there a question from our audience here? Was I think I saw a question. Do you hold on? Let me walk out so our online audience can also hear. You had one? You sure? Anyone?
No questions?
I have more from online. So
Online. Yeah,
let's
because
see.
they're flipping back and forth looking at.
Yes. Sorry, I have the online chat through my phone, so sometimes while I'm walking, I accidentally scroll and I'm like, oh God, where'd the question go? So the next question is, do you know why, although Hubble is a telescope that appears to be in a tube, like the ones we have here, why the James Webb is an open truss type telescope?
Okay, that's a good one. Think about where Hubble is located near Earth, and its light capability has to be uh, focused much more than Webb. Webb is 1 million miles out in orbit, where the light of the Earth and Moon are negligible compared to uh, the Hubble being so close to the orbit. So that's the big reason is the light gathering capability for the Hubble needed to be more focused in terms of a tube, but not as we do that on Earth. We have to do the same thing with the light because there's so much light around that a telescope has to have that blocking and only focus on the light that's coming in, while the the Webb telescope, being so far out in dark space, can just let it go, let the light that's there be used instead.
So probably a similar answer to why they now sell open truss type telescopes like through Celestron, Meade, to name a couple. But a lot of people, there's an aftermarket business of sewing these little like stretchy spandex sleeves that go over the open truss to protect it from the stray light.
That's it, the stray light, and the Webb telescope being that far out is not needing to have that protection. But it does bring me back to the point of what happens. Somebody over I ask, what happens if or when it will happen eventually. Something will fail in one of the systems, right? And how will we fix it? So
Huh?
that's going to be I think a movement up.
All right. So we got another question from here.
Why was James Webb worked on all across the world? Why wasn't it just worked on in like one lab?
I'm sorry, I can't hear. I couldn't hear.
So, why was it a huge collaborative effort across the world to work on James Webb versus just done in like one lab in
Oh,
the
right.
United States?
Well, there's just that many components made by different peoples. It's actually, I didn't really emphasize it, but it is a worldwide collaborative effort of the European Space Agency and the Australians, the New Zealand, the Southeast Asian, and the Americans. Um, but the different parts that it's just the systems are made by so many different people. Not like the rovers, right? The rovers, you're thinking like the rover, like Perseverance, that's mostly made here at the lab. But something as complicated, you saw the sun shield and the way that that opened up, and the way that it opens up to protect from the sun, to keep the temperature facing the sun and the temperature away from the sun moderated. There were just that many different components that needed to be manufactured and produced by those other places. Each one of them had their own little niche that that could be used. You know, we need this, we need that, we need an infrared sensor. Okay, we need processor. We need a dedicated circuit analysis, and each of those components needed to be made by somebody different. Yeah.
Plus, I would imagine there's a lot of companies throughout the world that are very specialized in some of this equipment, but not in others. And it's nice not having to reinvent the wheel at a lab if the technology is already out there.
Oh, and also the cost, right? The cost when you have to do it sole source, the time it takes and the cost. You can get a company that's already making that product. You don't have to make it yourselves, and they probably know a lot more about that product anyway, so that they can help in the integration of those components.
Right. So our next question is, now that the James Webb is up in space and deployed, is there another large telescope in the works?
That I don't know. That's one of those things where only the one that a select few would know if that were true. And we're talking like maybe three three people, if that was in the works. Other than that, that's one of those questions where, I wouldn't doubt if they're thinking about it, but I think we're gonna find out how well Webb performs. And so far, if you've listened to any of the media conferences or the teleconferences, it's a really unbelievable how perfect, near perfect, that the Webb deployment, the launch, the deployment, the calibration, the refinement has gone. It's been flawless, really flawless, and that's a testimony to preparation. Right, preparation prevents poor performance, and you prepare, and you continually prepare, and think of all these other components. That's why it's good to have more than one or two in a group. We like to have that group thinking in terms of solving problems. So successful.
Right. Was there another question from our audience here? Right. So our next online question was, and I guess it's more of a statement. So the mirror is smooth because of shrinkage. Like when things get cold here, they kind of shrink and contract down. So the mirror for the James Webb is smooth because everything shrinks and contracts down in space.
Well, no, it was actually done on Earth. We do that in the lab. That's done in the building. No. They shrunk the metal was done before it went into outer space. No, that was all done prior to that. No, don't think that we don't have that equipment. There are facilities at JPL where the temperatures can be made just as cold as outer space, and also the application of the gold too. The way that it was vaporized and applied, that the sensors that are there the deposition of the gold, very, very well measured and monitored as it was applied. Oh yeah, that was all done on Earth. But it is true that things do shrink. But
okay, so it was done as part of the process of making the mirror, not taking advantage of physics that we know would happen.
right, exactly. It's done more. It was done on Earth, all that, and tested and recalibrated if needed. Yep.
All right. So our next question is probably a bounce off of our previous question about the is there another scope, is do you ever get information sent to you that you cannot share with the public?
I've had that happen when when Pluto was downgraded at first. Right, that was a sore subject. People were very upset. Yeah, they were. And if they were protests about it. Um, and that was one of those where I was definitely told to be very careful about how it was explained. Yeah. Oh yeah, I made the news about that. I was in the newspaper because I had said something. I had said something about Pluto actually is part of the Kuiper Belt, and I said that at the time when the Astronomical Society decided to designate Pluto as what we call a dwarf planet, and a lot of jokes with Snow White and stuff. But yeah, it is a fact that the orbit of Pluto is so eccentric that in about 1,000 years from now, it will be completely in the Kuiper Belt. It won't be actually part of what we call the solar system, where most of those objects have been cleared. Yeah, that was one of those topics. Certainly, I was not allowed to share that.
All right. Is there a question here? Nope. All right. So the next question is there a possibility of plans of repair of the James Webb now that it seems that space travel will become more commercialized and accessible?
Well, that's a good one. Possibly. That's what we're hoping for, at least. That with the success of SpaceX, that traveling to a Lagrangian point will be something that will become like going to the moon. We'll be going to the moon.
Right. So we just have one more online question. I want to thank everyone here and just put out a last call for any last minute questions online so that while we're answering this last question, they have time to react and respond since the live stream is always slightly delayed. Oh, do you have another question here? Perfect. Let's do that one first.
I wanted to ask, do you think there'll ever be any like telescopes on the moon? Like
I'm sorry?
built? Do you think there'll ever be any telescopes built on the moon?
Oh, yeah, sure. Definitely. We'll have astronomers on the moon, just like we're here. As a matter of fact, that'll be probably part of the vacation. Yeah. You get an hour on the moon to look through the telescope to see Mars, or to see Jupiter, and look at the Galilean satellites, right? Europa and Io. Oh, yeah. Or the asteroid belt. We could see objects that clear there. Yeah, that's great.
Set it up like a hot honeymoon destination. Like they have those little. I honestly forget where what country it was in, but I keep seeing the images online where it's like you're in a little glass igloo and you can see like the aurora and whatnot, and you have the big bed. Iceland, you said? I don't know, but
Yeah.
man, that would be fun.
Those things we're getting there. I mean, slowly the need. I don't know if you ever watched the Cosmos series with Carl Sagan, and then Neil Tyson, as well. That our drive to explore and to search out for new worlds, Star Trek, right? It's there. that need. I certainly hope it will happen. I don't know if it'll happen in my lifetime, but what we're seeing with SpaceX and the redeployment of these rockets one after the other, safely returning, and then another 12 missions, 2 missions in 2 days. That's amazing.
Right. So our last question, it appears, since our chat team online seems to be good, is we always hear about the Hubble and the James Webb. Why don't we hear more about ones like the Spitzer, which you mentioned, or Chandra? Is it because they have been decommissioned?
No, it's actually because their focus was much smaller. Um, the, their I believe that that's the reason that their audience was less than. There was a specific audience that was looking at that, and the information that they provided was, or has been looked at, and though there are still groups that are studying it now, it's known, and we're now improving upon what was then to now with the web. But there's still important information. You'll still see articles about Spitzer and the Hubble. Oh, of course, Hubble still you could still use it. The download, those photographs and the graphs and the data that Spitzer and Hubble. It's the same thing with Kepler. You don't hear as much about Kepler until some group has looked at the data again and discovered something. That happened not too long ago.
All right. Uh, I actually have one question based on what you just said. So I believe Hubble has like a whole database of information and images that's accessible to the general public that amateur astronomers can uh, do what they will with for artistic or scientific purposes. Will the James Webb have a database like that for its data?
That hasn't been determined yet. We don't know, but I'm sure that it will be. Um, that's one of the things that if you're a scientist right now, you can propose to use the Webb telescope, and you have to have the data. But like the Hubble telescope, if you recall, it only took what, 4 years after it was deployed, where I know that there were some astronomers of the Princeton Astronomy Club who they applied to use it, and they were using it. That's in 96, 97, 26 years ago, 25 years ago. And that was open to the general public. They wanted to see something, they applied, and they were allowed to look at it. Yeah.
Right. And it looks like that was the last of the questions. I want to thank everyone who is both here and online again. Thank you, Michael, for a wonderful presentation. We hope to have you back. You could probably talk to me after stream about getting another slot later this year. And like I said, do check us out on our website, uacnj.org. That's where you'll find all of our information about our ongoing programs and where you can reach us with any of your questions and suggestions. And with that, everyone have a good night.
Thank you.